Welcome to Train Signal. You're watching a lesson on subnetting. Now, in previous lessons, we've learned about things like networks, and we've learned about IP addresses, and we've seen just a little bit about how maybe those go together. Well, in this lesson, we're going to see how we can take a network and subdivide it into subnetworks. So, subnetting, by definition, is the process of taking a large network and dividing it into smaller networks to increase efficiency and manageability. You may recall in a previous lesson when we were talking about IP addresses, talked about the idea of maybe having more computers within your local area network than you want to have in a single area of management. And there's a number of different explanations on what we mean by area of management. We may want to create what's called broadcast domains. That's one way of looking at area of management. A computer is broadcasting, or if X number of computers are broadcasting, how much of that traffic is being created because you have too many computers within that same network. Well, subnetting can help divide into multiple networks and create those broadcast domains. Or we could just be talking about pure IP management, keeping track of certain departments being on certain networks may make things easier for you when troubleshooting to know if you see a certain IP address, you say, oh, that came from a certain network. That came from a certain department. So an example that I could give you here is if you took a network of 172.16. Okay, you have this network here. And don't worry right now about how I came up with some of these numbers. I'm going to explain this to you. But I will tell you that the 172.16 network with a 255.255.0.0 subnet mask, that network is going to give us 65,534 hosts. That's what that network is going to give us. We may not want to have 65,000 computers on one single subnet, on one single network. So what we have the ability to do is if we're working within that 172.16 range altogether throughout the entire company, is we could break it down and say, all right, let's move our subnet mask over. We're going to move the dividing line where the network ID and the host ID is, and we're going to now make it 255.255.255.0, and we're going to say that the first subnet within this big 172.16 network is 172.16.1. Okay, so we're saying that all computers that start with 172.16.1 are now part of a network of their own, which has now narrowed us down to only 254 hosts that could be used on that network. Now, it doesn't mean you have to use 254. I mean, quite frankly, even with the 65,000, you don't have to have 65,000. It's just that that's what it can handle. And then we could create a second subnet, a third subnet of 172.16.2 and .3, each of which can have only up to 254 hosts, something that is much more manageable. Now, I mentioned in a previous lesson that we were going to talk about something called class-full IP addressing. And so this is where I want to talk to you about it. Originally, our IP addresses were divided into what's called class ranges. We had an A, B, C, D, and E class range of IP addresses. The A class range of IP addresses you could recognize because the first number in that IP address was somewhere between 1 and 126. And I will tell you, by the way, if you were to break down what I'm about to show you into binary, it would kind of make sense. You can see why the dividing lines are where they are. But for right now, I want you just to remember the numbers 1 to 126. And in an A-class range, the subnet mask that is used is 255.0.0.0. And that's what I made reference to in the previous lesson. I made reference to the fact that you might be able to assume a subnet mask based upon class-full IP addressing. If you want to assume that it's being used, and you have an IP address that starts, let's say, with the number 10, then you're assuming it's an A-class range and therefore is going to have a subnet mask of 255.0.0.0. The B class range will always begin with 128 to 191. I want you to notice that there is a number missing between the A class and the B class, and that number is 127. You may remember from the IP addresses lesson that we talked about the fact that the 127.anything range is not available for use. It has been reserved for diagnostic use only. Okay, so it's for that reason it doesn't fall into either the A or the B class. And in the B class, you get a subnet mask of 255.255.0.0. The C class range is 192 to 223. And again, that's the number you'll see in the first octet, that first number in the IP address. You have subnet mask of 255.255.255.0. And really, those are the three that I want you to focus on, because the D class, although it does exist and it has the IP addresses starting with 224 to 239, the only thing I want you to know about it is that this is used for multicast. Okay, so multicast transmissions, the way that those work are by using D class IP addresses. And then the E class range is for experimental use only. Okay, so again, beyond anything that you or I would participate with. Okay, so don't worry about the E class at all. For the most part, don't worry about D class other than that it's multicast. Now let's go back to the A, B, and C class for a moment here. With the A class, there are 126 networks available, right? Because we said it's anything starting with 1 to 126. And because the last 3 octets can be used for the host ID, that means that even though there are only 126 of these A-class networks out there, each one of them has almost 17 million IP addresses available. The number is actually 16,777,214. In your B-class network, there are 16,384 of those. In other words, if you start adding them up, you do the math of all the possible networks, starting with 128.0, and then you say 128.1 and 128.2, all the way through to 128.255, and then you move on to 129.0, 129.1, and you get all the way up till you get to 191.255. There's 16,384 of them. And because the last 2 octets can be used for your host ID, you can have up to 65,534 hosts in each one of these networks. In our C class range, because the 3 octets are used for the network ID, and you can use anything from 192 to 223 for the starting number, you end up with a little over 2 million of these networks, but each one of these networks only allows for 254 hosts. This, by the way, is where my example came from. When I said an example of using the 172.16 range, you have 65,534 total hosts. But if you break those down into subnets, you'd get 254 each. That's where those numbers came from. Now, the other thing that I'm going to tell you, and I don't want to go too deep into this, is when it comes to A, B, and C class, and the number of networks and the number of available IP addresses in each of those networks, this was how things used to work with the internet. If you wanted to get on the internet, so you're representing your company, you want to have an internet presence, you would actually register to get one of these ranges. You would actually have an IP range that was assigned to your company. The problem was we ran out, right? I mean, if you do the math here, there's only a little over 2,100,000 networks total between A, B, and C class. On top of that, we also only have a total of just under 4 billion total hosts available. And that is something else that we also ran out of. Now, I already talked to you in another lesson about how we addressed this issue of running out by using private IP addressing, right? Using the private ranges that are not available for internet use. And that the only companies that truly need to have these live internet addresses are the internet service providers, and then they can divvy up those individual addresses out to all of the individual companies, right? To you and to me. And guess what? You know how they divvy them out to us? You know, they divvy it up by subnetting. Okay? Because again, they need to have more than just the little over 2 million options available, because there's more than 2 million companies looking for a range of IP addresses. And when I say companies, guess what? You at home, if you want internet access, it's almost like you're a company. You need to have one of these live IP addresses. You got to have one of these A, B, or C class addresses. So the ISPs take care of that at this point. So now I mentioned that class full IP addressing was kind of a thing of the past. Well, the reason it's kind of a thing of the past is because there's a lot of problems when we exclusively use class full IP addressing. And the problems stem from the fact that you have these huge gaps in what's available in each range. Okay, so with your class A range, you have almost 17 million hosts. Then your class B range, you jump all the way down to 65,000 hosts. And then your class C range, you have another huge jump all the way down to 250 hosts. And yes, I know these numbers aren't exact. There are some little numbers that we've talked about. But you get the idea. There's these huge gaps. So what happens if you fall in the middle of those gaps? So the example that I have here is what happens if you have 2,000 hosts, right? You're in a company of approximately 2,000 people. Each one has to have a computer, and they each have to have an IP address. Now what do? Well, let's see. You got a couple choices. One choice is you could go ahead and get 8 Class C ranges of IP addresses. Right? Do the math. That's just over 2,000. All right, so you should be able to take care of it. Maybe you grab a 9th one if you need to, if that's not quite enough. But when you do that, you are grabbing, these 8 or 9 literal ranges out on the internet, which means you're going to end up with cluttered routing table entries. It gets kind of crazy because you have all these different networks that are registered to you. Or another option is you say, well, I don't want to hassle with all of that. Let's just go ahead and get a Class B range. Why not? And I will tell you, that's what most companies did. If you had a few thousand hosts that needed an IP address, you just went ahead and jumped to a Class B. But now what? Now you're tying up 65,000 hosts, or to be more specific, 65,000 IP addresses, when you only have 2,000 hosts, which means what? 63,000 some odd IP addresses are just sitting out in Never Never Land. Can't be used. I'll tell you what, when I first got into this business, if you go back to the 1990s when I first started, the place where I worked, that's exactly what we had. We had a Class B range assigned to us, and we were nowhere near 65,000. I think we were bigger than 2,000, but I'd be willing to bet we were no more than 5,000. That's a lot of wasted IP addresses. So when you hear about things like, well, we're running out of IP addresses, or we ran out of IP addresses, this is why. And one of the solutions, you like how I did that with 1, but I held up 2 ones? Okay. One solution to that is something called classless interdomain routing, or CIDR, C-I-D-R. So let me explain exactly how that works. So with the use of classless interdomain routing, or CIDR, or the way I pronounce it is CIDR. I've heard some people call it CIDR. Either way, it's fine, as long as you know it's CIDR, or more specifically, classless interdomain routing. With the use of variable length subnet masks, VLSM, we can resolve this whole issue of a company with 2,000 addresses needing to be assigned, either 8 different 254 range IP networks or a 65,000 IP range network. When using decimal, when using the decimal numbering system, we learned that the subnet masks always have 255s or zeros. But the reality is that what that actually represents in binary is the 255s is all ones, right? If we convert the number 255 to binary, we get 1, 1, 1, 1, 1, I don't know, 8 ones. And if we convert 0 to binary, well, then it's all zeros. If we look at an IP address, and therefore the corresponding subnet mask, in binary, then instead of only being able to draw the line on the specific individual dots, we now have the ability to go ahead and move this line back and forth in between any particular 1 or 0. Okay, we can move it wherever we need to move it. And so using variable length subnet masks, what that means is we still have to have all ones on the left and all zeros on the right. But because we might end those ones in the middle of one of those octets, not only will we have subnet masks including the numbers 255 and 0, but we might also have, as we see here, the numbers 254, 252, 248, 240, 224, 192, and 128. If you have internet at home and you've ever paid really close attention to what your IP address is from your internet service provider, you've probably seen a subnet mask that includes some of these numbers. So the idea here is if you had, and again, this is mostly being done at the ISPs at this point, but if you had that B-class range of IP addresses, meaning you have some range that uses the subnet mask of 255.255.0.0, but you need to divide this into smaller networks. Originally, over here on the left, we have a network ID of 16 ones and a host ID of 16 zeros. If we wanted to, the example on the right, I have subnetted to where you take, in this example, you'll see where I'm heading with this, I took 5 of those zeros from the host ID and I moved them over into the network ID, or what some people will refer to it as that small section being the subnet ID. Now, there's a formula that you need to use so that you can determine how to do this. In other words, where do we want to move that line? There's 2 main questions you need to ask when determining how to break down a big network into a bunch of subnetworks. The first question is, how many subnets do we need? In other words, how many different networks do we need? And then the second question you need to ask is, how many addresses do you need, or how many computers are you going to need to be able to support in each of those networks? And then you use a formula that says 2 to the nth power, okay, so 2 to the nth is an exponential number, and n is the number of ones that you're going to use in the subnet ID. That's the number of subnets that are available. When it comes to the number of available hosts that you can have within each network, it's a slightly different formula. It's 2 to the n minus 2. And the reason that it's minus 2 is because, remember from IP addressing rules, you cannot have all zeros or all ones in your host ID. So n represents the number of zeros that are going to be in the subnet mask making up the host ID. You take that, 2 to that number, subtract away 2 because you can't use all zeros or all ones, you get the number of hosts that are available. Now I have an example here, and I understand, by the way, that this happens to be very confusing material. My hope is that by the end of this lesson it all comes together. It's very difficult to teach this in a piece by piece and you grasp each piece until you understand the next. But the example I give here is where, remember how I took 5 of those zeros and I turned them into ones? Well, in that example, we could say 2 to the 5th power, right? Because we borrowed 5 ones into the subnet. 2 to the 5th equals 32. So that's 32 individual networks I can now support. But more specifically, I want to point out the fact that after taking away those 5 zeros, we're left with 11 zeros, representing the number of bits that are going to be in the host ID. And 2 to the 11th minus 2 is 2,046 available hosts in each of those subnets. Why did I go to that specific example? Well, the reason is because I also gave you an example of a scenario just a few moments ago where you have a company with 2,000 computers. And what was your choice? Your choice was either to get 8 of those Class Cs or 1 Class B. Well, here I'm talking about how you can take a Class B, and we could say the ISP can do this. The ISP could have this Class B network, could subnet it down to where they hand you 2,046 IP addresses. Now, in a previous lesson, we learned all about IP addresses, and there were certain rules with those IP addresses. And I mentioned with those rules that some of them kind of had to do with the binary aspect of an IP address. Well, I want to review a few of those with you right now. I had said that in an IP address, each of the 4 numbers is technically called an octet, representing that it is an 8-bit number. And because it's binary, each one of those bits can either be a 1 or a 0. And then from there, each octet, okay, so each one of these numbers, can only have a number from 0 to 255. And from the binary math lesson, you should understand why, because if you had 8 zeros all in a row, that would be 0. If you had 8 ones in a row, that would convert to 255. Okay, so that's why that's your full range. So I want you to keep in mind, once again, that each of the numbers that you see in an IP address, although you and I typically look at them in a decimal fashion, we see things like 192.168, etc. It's actually looked at by the computer in binary. Now, because of that, we need to make sure that we fully understand how IP addresses work in binary. So to truly understand everything that has to do with subnetting and IP addressing, you have to be able to do this in binary. As I mentioned before, if you have all zeros, okay, and so I've actually put it on the screen for you, all just like we had in the binary math lesson, where we have all these zeros going across in every column, well, that equals 0. Whereas if we were to put ones in every column and add all those 8 columns up, you end up with 255. That is why we say that each number in an IP address can only be from 0 to 255. It's because of the binary math. Okay, so it's so important to be able to grasp onto that. If we take an IP address that we recognize as 192.168.10.101 and convert it to binary, we do this by taking each octet. So we start off with 192, convert that to binary, and we get 11000000. We take 168, convert that into 10101000. We take 10 and convert that into 00001010. And by the way, in the binary math lesson, we didn't worry about preceding zeros, right? We didn't worry about a number beginning with a bunch of zeros. We always started with a 1. Well, here, when we're talking about octets, it's a literal 8-bit number where 10 is going to be converted to just simply 1010. You have to add the preceding zeros to make it an 8-bit binary number. And we take that 101 and convert it into 011000101. And you put it all together, and what do you get? This big, long, 32-bit binary IP address. Now let's do the same thing with subnet masks. It's not that hard. We always have ones to the left, and we always have zeros to the right. That's why we always have 255s and zeros, unless we're going to use variable length subnet masks, where we might also get some of those other numbers if we are stopping the ones and starting the zeros somewhere within an octet. But when you put it all together, you take your IP address and subnet mask and put it together, this is what it looks like. And anywhere you see ones in the subnet mask, that's your network ID. And anywhere you see zeros, that's your host ID. So let's go back to a simple network. But I've made one slight change here. I've made it that my client is 192.168.10.101, server's 192.168.10.201, and the firewall routers, or at least the inside of it, is 192.168.10.200. Those look like they're all on the same network, right? They look like they're all on the 192.168.10 network. But here's the problem. Look at the subnet mask. It used to be 255.255.255.0, but because I have subnetted, I've changed the subnet mask to 255.255.255.248. And guess what? By doing that, believe it or not, this is the example of a bad network. So why isn't my network working, right? If we have this network, which looks like it should be fine, why isn't it working? Well, the easiest way to break this down, and this is why it's so important and why it's so insistent that you learn this, is we need to take all 3 of those IP addresses and break them down into binary. So I've taken the client, the server, and the router, and I've put them all in binary. And I've taken the subnet mask and put it in binary. And what we need to do is we need to make sure that Anywhere there are ones in the subnet mask, which you'll notice even though 192.168.10 should be a Class C network, which means it's just 222.55.0, we subnetted. So believe it or not, the subnet mask gets continued all the way for those 5 additional ones into the last octet. That is the entire subnet mask, and that is where the network ID portion of all 3 of those IP addresses needs to be. And if they're going to talk, they need to all be on the same network. So take a look. If you look at them, you'll notice that they're almost all the same, but the top one, the client IP address, is just a little bit different when we get near the end. Okay, as soon as we get to that 01100, it's different than the 11001 of the other 2 computers. So therefore, they are not all in the same network. So how do we fix this? Well, if we're going to use a subnet mask of 255.255.255.248, each network is going to be broken into blocks of 6 host addresses. So I gave you one example here. All right, we start off with, if we're going to do 192.168.10, the first network that we could use would be if that subnet area, right, where we have the 5 bits that we borrowed, we're going to make those all zeros, and then we're going to put in all 8 possible combinations that can follow, right, which is anywhere from 000, 001, 010, and so on and so forth, all the way down to where we get 111. Those are the 8 possible combinations. And if we were to convert that back to decimal, you'd see that that's 192.168.10.0123456 But I said there can only be 6 host addresses. And the reason why is because we can't use all zeros or all ones. So the top line, where you have all zeros in the host ID, and the bottom line, where we have all ones in the host ID, those can't be used. The remaining 6 in the middle are the ones that are used. 192.168.10.1, 2, 3, 4, 5, and 6. And again, just to review, the reason you can't use the top one is because that actually represents the network ID, 192.168.10.0. And the bottom one is the broadcast ID for that network, 192.168.10.7. To continue that example, if we were to go to the next block of IP addresses, we would use everything exactly the same as far as 192.168.10, but that in our subnet range, we're going to change that to 00001. That's the next progressing network that's available. Use all 8 combinations again of the host ID. Okay, you take away the top and the bottom, and you end up with the 6 addresses you can actually use. 192.168.10.9, 10, 11, 12, 13, and 14. So here, you'll see, to fix this problem, I have grabbed hold of a block of IP addresses, and you'll notice that these IP addresses are all valid in that first range that we did. So we can use 192.168.10.1, 2, and 3 and have our network work. So if we take a look at the diagram, you'll see that if I simply make the client 192.168.10.3, the server 10.2, and the firewall 10.1, now our network has been fixed. Now, there's one last thing that you need to know when it comes to classless interdomain routing, and that is something called a CIDR notation. Okay, and this is not anything new when it comes to understanding what CIDR is. It has to do with the way it's represented, okay, the way somebody might write down an IP address or the way an operating environment might represent an IP address. Now, the old way, without CIDR notation, we used to just put an IP address and its corresponding subnet mask. So the example might be 192.168.10.1 for the IP address, and then 255.255.255.248 for the subnet mask. With this new CIDR notation, we can summarize that by putting the IP address and then putting a slash and a number after the slash representing the number of ones in the subnet mask. And remember, the subnet mask is going to be a bunch of ones until it gets to a point, and then it's going to be zeros. And if we know that there's a finite number of bits there, which we know is 32 bits, right? We have our 4 8-bit octets. 4 times 8 is 32. Well, if we go ahead and establish there's X number of ones, then we also know there's X number of zeros by just subtracting it from 32. So the example of a CIDR notation here might be 192.168.10.1/29. Okay, and that, again, that /29 is because we had 255.255.255.248. Each of those three 255s is 8 bits of ones, right? So that's 24 ones. And a 248, when we convert that, it turns out to be 5 ones and then 3 zeros. You add the 5 ones to the 24 we already had, you get 29. Okay, so make sure that when you see this CIDR notation that you really understand what it means. Because I'll tell you, I've had a lot of people, and I'm talking about seasoned veterans, who have walked up to me and said, I don't know what that means. What does it mean when you have this IP address what's the slash number? You got to know what it means, because more and more people are going to start using it, and more operating environments and different services and things like that are representing with the CIDR notation. Now, not only do you need to know about the CIDR notation, but you got to know subnetting, because that's the end of this lesson. All right, so you need to know how, for the purposes of not wasting IP addresses out on the internet anymore, and then also for perfectly fitting the needs within your organization, how to take a network and subdivide it into multiple networks. And to take that a step further, the whole reason that I've emphasized the need for understanding binary, right? We had a whole binary math lesson. Well, that's so that you can further take this subnetting right down to a real defined point that you need to satisfy those needs. So that's all I have for you. I'll see you in the next lesson.